Inferential statistics, or statistical hypothesis testing, is all about using a limited sample from a population to make inferences about that entire population. We don't just describe some population parameter, some aspect of the population we're interested in. We use a sample statistic to decide something about that population parameter. To do this, we specify statistical hypotheses about the population, a null hypothesis and an alternative hypothesis. In this video, I'll explain why we need a null hypothesis. Let's start with an example. I recently started reading about raw meat diets for cats. Suppose I want to test whether a raw meat diet is healthier for cats than regular canned food with cooked meat and grains. I could ask all my students with cats to participate in a study where half is randomly assigned to feed their cat raw meat, while the other half provides canned food. After 2 months, a veterinarian determines the cat's health by analyzing blood work and stool samples, resulting in a health rating between 0 and 10. If diet is related to health, the two groups will come from distinct populations, one with a higher mean health value than the other. I expect the mean of the raw group minus the mean of the canned group to be larger than 0 if raw meat truly results in better health. Suppose I find a sample difference between group means of 1.12. This difference looks pretty big, so why can't we just infer there's a real effect of diet in the population? Well, it's possible that it's a chance finding. The true difference may be over- or underestimated because the samples aren't perfectly precise representations of the population, simply due to chance. So we want to take chance into account. Chance, or lack of perfect precision. If our sample statistic is less precise, our decision has a larger probability of being incorrect. We introduce probability by asking, if we were to sample indefinitely, what would the distribution of our sample statistic look like? This is useful because if we know what the distribution looks like, we can say what the probability of a certain range of sample statistic values is by looking at the area under the curve. So if we know the distribution, we can determine probabilities and make a more informed decision. The shape of the distribution is determined by the type of statistic we're interested in. Statisticians like Fisher, Pearson, Gossett, Nyman, they've all shown that proportions, means, differences between two means, differences between more than two means, they're all associated with differently shaped distributions. The shape is also affected by the sample size and variation in the population, which influences the precision of the sample statistic. Bigger samples provide more precise estimates of the population parameters. Large variation in the population results in less precise estimates, so a wider sampling distribution. By dividing the sample statistic by the standard error, we correct for variation in sample size. The sampling distribution for our particular sample is turned into a standardized probability distribution. Now we know the shape and the scale of the probability distribution. It would be great if we could now say, for example, that based on the sample difference of 1.12, the probability that a true population difference favoring a raw diet exists is 0.32. Except it doesn't work that way, at least not using frequentist statistics. We simply can't calculate this probability because we don't know where the probability distribution lies. We know the shape and scale, but not the location, which is determined by the population mean. The only way to pin it down is to make assumptions about its exact location, which means, at best, we can calculate the probability of finding a sample difference of 1.12, assuming the true population value is exactly X.